So, have you ever stopped to wonder if the universe has a sound? Not sound like we know it, but something way deeper, ripples in the very fabric of space and time. Well, today, we're diving into the absolutely incredible science of gravitational waves. Einstein actually predicted these things over 100 years ago with his theory of general relativity, but for decades, that's all they were, just a theory. So let's get right to it. What exactly is a gravitational wave? Okay, the best way to picture it is to imagine dropping a pebble into a perfectly still pond. You see those ripples spreading out, right? Now just imagine that the pond isn't water, but the entire universe, what physicists call space-time. And the pebbles? Well, those are the most massive, most violent events in the entire cosmos. To get a little more technical, whenever you have truly massive objects, we're talking black holes, neutron stars, and they accelerate, they create a disturbance that travels out at the speed of light. But here is the mind-bending part. These are not waves moving through space. They are waves of space itself. Space-time is literally warping. So what happens when one of these waves, after maybe traveling for billions of years, finally gets here to Earth? Well, it does something very, very specific and very strange. This is a wild idea to wrap your head around. As a wave passes right through you, which it's doing right now, it doesn't push you. It actually changes the amount of space between you and everything else. It alternately stretches and then squeezes the very fabric of space.
This little animation shows us exactly what's happening. If you imagine a perfect circle of particles just floating in space, as a gravitational wave passes through, you'd see the circle get squeezed in one direction while it stretches out in the other.
And then, just a fraction of a second later, it flips. The direction that was just squeezed is now being stretched, and the direction that was stretched gets squeezed. It's this rhythmic back-and-forth distortion that scientists are hunting for. This incredibly specific pattern is so unique that it's known as the signature of a gravitational wave. If you can somehow measure this exact motion, you've found one. But that, of course, leads to a really big question. I mean, if these waves are constantly warping the very space we live in, that brings up a pretty obvious point, right? Yeah, why don't we notice the room getting a little wider, then a little taller, over and over? Why isn't everything around us just constantly wobbling like Jell-O? And the answer is just staggering. The change is so unbelievably tiny, so infinitesimally small, that it's completely impossible for us to notice. It's even impossible for most of our best scientific instruments to notice. This is the number we're talking about. It's called the strain, and it represents how much the distance changes. That's a decimal point followed by 20 zeros and then a 1. It's a scale that is almost impossible to even imagine.
Let me try to put that into perspective for you. To detect a gravitational wave, you have to be able to measure a change in length over a 4-kilometer distance, that's about 2.5 miles, that is thousands of times smaller than a single proton. For a long time, this challenge was considered so huge, many people thought it was just plain impossible.
So how in the world do we pull it off? How do you measure a change that's almost nothing, with a precision that just seems to defy reality itself? Well, the answer was an incredible device called a laser interferometer. It's an absolutely ingenious machine that uses the properties of light to make probably the most precise measurement humanity has ever attempted. So here's the basic idea. It's a huge L-shaped machine. You shoot a laser at something called a beam splitter, which does exactly what it sounds like. It splits that one beam of light into 2 identical copies. Okay, so here's the play-by-play of how it hears a wave. Step 1, that laser beam gets split in 2. Step 2, those 2 beams travel down 2 really long arms at a right angle to each other. Step 3, they hit super precise mirrors at the end and bounce right back to where they started. Step 4, they get recombined at a detector. Now, if the arms are perfectly identical, the 2 light waves should cancel each other out completely, and the detector sees nothing. But, and here's the magic, step 5, if a gravitational wave passes by, it stretches one arm and squeezes the other. That tiny, tiny change means the light waves are no longer perfectly in sync when they come back. They create a new pattern, and that is the signal. That's the wave. And this is what that simple diagram looks like in reality. This is LIGO, the Laser Interferometer Gravitational Wave Observatory. And no, those aren't roads. Those are 4-kilometer-long concrete tubes that hold a near-perfect vacuum for the laser beams to travel through. It is genuinely one of the most incredible machines ever built.
You see, when scientists finally detected the first gravitational wave back in 2015, it wasn't just the end of a very long search, it was the beginning of a true revolution in how we look at the universe. Think about it this way. For all of human history, everything we've learned about the cosmos came from looking at light. Visible light, radio waves, X-rays, you name it. We have only ever seen the universe. But now, for the first time ever, we can actually hear it.
This opens up a whole new way to experience the cosmos. We can now listen in on things that are completely invisible, like two black holes smashing into each other. And unlike light, which gets blocked and scattered by gas and dust, these waves travel across the universe almost completely undisturbed. They're like perfect little messengers, carrying secrets from the most extreme events out there, giving us a direct line to things we never even knew were happening. We've spent centuries just looking at the stars, but we have only just begun to listen. This amazing new sense is going to let us probe the deepest secrets of black holes, the hearts of dying stars, maybe even the very echoes of the Big Bang itself. The age of only seeing the universe is over. The age of listening has just begun.